Now that we understand what mass is, let us try to do some numericals based on mass. Okay, so that is very important that we are able to solve the numericals. That is actually how the questions are asked. So just learning what mass is not good enough. We have to be able to solve some numericals. So here is a numerical from our book in which we are being asked to find the mass density of the sodium atom. So what is mass density? Or simply if we call it density, it means mass per unit volume. So if I take a unit volume of sodium atom, let's say 1 meter cube, then how much mass in kilogram would be present in it? So for that, all I need to do is that I need to calculate the total mass of the atom divided by total volume of the atom, and that would give me the mass in kg per meter cube. If the volume is in meter cubes, and the mass I have calculated in kg. So very, very simple. I only need two terms. I already have provided the size of the atom. Now, what is the size of the atom? See, size of the atom, we'll just assume that the atom is a sphere. It is very similar to a sphere like this. That's what we will assume. And if we assume the atom to be a sphere, and we are given its size, we are being given its diameter of the sphere. So all we need to do is that we need to find the radius of the sphere, and that radius would of course be, if we just find the radius, this radius would of course be half the diameter, so this will be 1.25 angstroms. And from this radius, we will then be able to find the volume of the sphere. So let's just first find out the volume of the sphere, what that would be. Very, very simple. We already know the volume of a sphere is 4 by 3 pi r cube. In our case, we know the value of 4 by 3. Of course, it's 4 by 3. And then 3.14 will take the value of pi. And then we will multiply it with r cube. So what is r cube? R cube for us is 1.25 angstroms. So we'll straight away convert this into meters. And this will get 1.25 into 10 to the power of minus 10. We have converted into meters the whole cube. So that is the volume of our sphere. If you compute this entire number, this would come out to be approximately 8.125 into 10 to the power of minus 30 meter cube. So we were able to calculate the volume. Very, very simple. Now let's just compute the mass. For computing the mass, we observe that the sodium, see here we are dealing with the sodium atom. Okay, so we have to only consider the atomic mass of the sodium. So we can consider that. We'll just ignore the electrons for a little while, and based on the mass number, we will just say that we already know that if I take 1 mole of this sodium atom, so that is 6.023, okay, we'll just take 6.02 if you will, okay, of this sodium atom into 10 to the power of 23, sodium atoms actually weigh 23 grams. Okay, that is from the Avogadro's hypothesis. We can say that this is what it would be. Now, from there, we can find out that one of these atoms actually weighs 23 divided by 6.023 into 10 to the power of 23, and this is of course still in grams. So if I divide it by 1000 more, then I know that this number I have achieved in kilogram. That is what I need. See, we'll always use the SI units. Nothing complicated here. We are not doing anything special. If you compute this comes out to be the M mass of one of these atoms comes out to be 3.81. I've already pre-computed this so that we don't waste our time, into 10 raised to power minus 26 kilogram. Now, all I need to do is I need to divide the mass by this volume, and we will have our answer. So our density of the atom, as we have computed it, is equal to mass by volume, which is 3.81 into 10 to the power minus 26 divided by 8.125, which we computed earlier, the volume, into 10 to the power minus 30 kg per meter cube. And this comes out to be very large. Actually, it comes out to be, our estimate actually comes out to be very, very large, and it comes out to be 4,680 kg per meter cube. Now, this is to be expected when in crystalline phase. What does it mean by crystalline phase? When we take the crystal of, for example, sugar, when we take crystal of salt, the atoms there are arranged very, very nicely in periodic fashion. So here we have just taken a lattice. It is one cell. Okay, this is a part of the sodium crystal. That's what we have taken. And here, this is how the atoms are actually arranged. So notice that when I arrange atoms in this crystalline form, when I do that, notice that here we have the atoms arranged, and if you notice closely, the atoms are spheres. But when we arrange them in this nice fashion in row wise and column wise, then there are gaps left here. So of course, because of these gaps, the density will definitely reduce, and hence it will not be the same as the atomic density. Not only that is not the only problem. Another problem that we have, as we can see in the figure, is that the atoms are not next to each other. There is a gap here. And because of this gap also, the density will actually reduce. So those are the reasons why the crystalline sodium has less density than the individual atoms of sodium might have. Let us just try to find out the density of this crystalline sodium. Let's just try to compute it. For that, we need one dimension, which is what is the distance between these two sodium atoms. So this is one sodium atom, this is the second sodium atom. And what is the distance between these? So this is a cube in which we have one full atom and 1/4 atom. So 1/4, 1/4, 1/4. So in this cube, there are total of 2 atoms of sodium. And what is the length of the side of the cube? See, that we can actually look up. It's given everywhere. It can easily find it. This comes out to be 4.2 angstroms. Okay, so 4.2 angstroms. I just use the darker color. So this length of the site is 4.2 angstroms. In this 4.2 angstroms, we can then compute the volume of this lattice. So what is the volume of this lattice? It is 4.2 into 10 to the power of minus 10, the whole cube. Okay. What about the mass? What is the mass of this lattice? Total mass is actually the mass of 2 atoms. Very, very simple. Nothing, we are not doing anything special. So the mass of this cube is actually equivalent to mass of 2 sodium atoms. And we know the mass of 1 sodium atom was this much. So we multiplied with 2. And this is of course in meter cube. So what about the density of this particular section of the sodium lattice? The density of the sodium lattice would therefore, if we compute it, it would come out to be, so we'll just say density of the lattice is ml, the mass of the lattice, divided by the volume of the lattice. Now nothing is special here. We know the mass, we know the volume. So this will of course be, mass will be 2 into 3.81 into 10 to the power of minus 26 divided by the volume, which is 4.2 into 10 to the power of minus 10, the whole cube. If you compute this, this will approximately come out to be 1025 kg per meter cube. Now we are very close to the real answer of 970. So the physics actually works. I mean, it's nothing surprising, but the physics should actually work. Okay. So here we have solved 2 problems which were based on the masses. So these are the kinds of problems you have. Here's another problem. In this case, we are being asked to find the nuclear mass. So previously, what we found the atomic mass. We found the mass when the atoms are arranged in this nice fashion in a crystalline lattice, like atoms in a sugar, atoms in a nice crystalline fashion when sodium atoms are arranged like that. So we found the mass of that. Now we are being asked to find the nuclear mass density. So we found the mass density. Now the nuclear mass density. Now nuclear mass density, what they are first telling us is that we need to show that it's independent. Is completely independent of the type of nucleus. No matter which nucleus I take, it is always the same. The mass density does not change. In other words, it does not depend upon the mass number. Right? That is what changes in the nucleus. That is what gives the nucleus its mass. It is the mass number of the atom. So if I say that the nucleus density is independent of the mass number, I have shown it that it is same for all the nuclei or all the different kinds of atoms. So to do that, we have a relation which tells us that the R nucleus sizes, the radius of the nucleus is actually equal to R0 into a raised to power 1 by 3. Okay, that is just the nucleus size, the size of the nucleus, okay? The radius of the nucleus. Again, if we assume the radius nucleus to be a sphere, then the volume of nucleus comes out to be 4 by 3 pi. We'll cube this one, and this will come out to be R0 cube. And here we will have a raised to power 1 by 3 cube. So just means that we'll just multiply this with 3, the power by 3 and 3 would cancel. So this will be a raised to power 1. So this is the volume. What about the mass? This is the volume of the nucleus. What about the mass? See, the mass, we already know that if we take the Avogadro, the 1 mole of these nuclei, then their mass would be equal to A. Okay. So if I want to take the mass of one nucleus, I just simply need to divide it by 1 mole. Okay. So that is the mass of one nucleus. Okay. I'm just dividing the mass number by the molar, the constant 6.02 into 10 raised to power 23. That is very, very simple. Okay. So what about the mass density? That of course comes out to be mass by volume. And this we'll compute it. Mass is given here. So this is A by 6.02 into 10 to the power 23. Okay. And this is in grams. Okay. So this is of course in grams. And then we have our volume, which is 4 by 3 pi R0 cube into A. Now this A and this A would of course cancel. Okay, so that is very, very simple. We know that the A and A would cancel because they are both appearing on the top. So our density of the nucleus, if you want to compute it, this will come out to be, this is in grams, but we want in, so this is gram, and this R0 has been given in Fermi. Okay, so we'll just keep the units as is, and later on we'll change the units. Okay, very, very, we will not make things complicated. Okay, we'll just keep it very, very simple. So this comes out to be 1 divided by and this R0 is given to be 1.2 Fermi. Okay, so this will be 1.2 the whole cube, and the units here, as far as we are concerned, okay, that is very, very important that we keep track of the units, otherwise we'll be lost. This will be in gram per Fermi cube. Okay, that is the units that we have been doing so far. Now I can easily convert these numbers, okay, to the various kilograms, right? So for example, to convert it to kilograms, all I need to do is I need to divide this by 1000, so that would convert to kilogram. Okay, I just change the pen of color and divide it. Okay, and to convert this Fermi cube, I really want to convert this Fermi cube into the our normal length, units of length, for example meter. I need to multiply it by 10 raised to power 15. So at the top I will write 10 raised to power 15, but of course this is not just Fermi, it's Fermi cube. So at the top the power would come out to be 10 raised to power 15 the whole cube. Okay, so that is what this would come out to be. And of course if I compute this, this would come out to be a very, very large number. So this would be of the order of, so we'll just write the order of, very, very simply, of 10 raised to power 17. Okay, so you can compute it yourself, find the exact value, but that is the rough order of this quantity. So it is very, very large. And of course, the nucleus has to be very, very dense, because we know that almost all the mass of the atom is concentrated in its nucleus. Nucleus is very, very small as compared to the atom, very, very small as compared to the atom, and therefore the atom has lot of empty space. So the nuclear density has to be very, very large and compared with the atomic density that we did earlier. Okay, so earlier we were dealing with the atomic density. Now we are dealing with the density of the nucleus. So it's an order of magnitude larger than the atomic density for the sodium atom that we actually computed. But of course, with this, we have computed the nuclear density of all the nuclei, because as we said that it is independent of the mass number. Okay, so very, very simply, we have just computed it. So hopefully these two numericals give you feel, okay, and I recommend that you solve these numericals yourself, try to find out the answer. You can use the calculator if you are having difficulty. If you don't use calculator, it's even better, try to estimate it like we did here. But if you have to use calculator, use it, but do solve the numericals yourself. Thank you.